it known to all and sundry that Ralph Parker is hereby appointed a member of the Little Orphan Annie Secret Circle and is entitled to all the honors and benefits occurring thereto.
Signed, Little Orphan Annie. Countersigned, Pierre Andre, in ink. Honors and benefits already at the age of 9. Come on, let's get on with it. I don't need all that jazz about smugglers and pirates.
Listen tomorrow night for the concluding adventure of the Black Pirate Ship. Now it's time for Annie's secret message for you members of the Secret Circle. Remember, kids, only members of Annie's Secret Circle can decode Annie's secret message. Remember, Annie is depending on you. Set your pins to B2. Here is the message. 12, 11.
I am in my first
8,
secret meeting.
5, 14, 11, 18, 16.
Oh, Pierre was in great voice tonight.
12,
I could tell that tonight's message was really important.
3, 25. That's a message from Annie herself. Remember, don't tell anyone.
90 seconds later, I'm in the only room in the house where a boy of 9 could sit in privacy and decode. Aha, B. I went to the next. E. The first word is B. S. It was coming easier now. U. 25. That's R.
I'll be right there, Ma! Gee whiz!
T. O. Be sure to. Be sure to what? What was Little Orphan Annie trying to say? Be sure to what?
Annie has got to go. Will you please come out?
All right, Ma! I'll be right out!
I was getting closer now. The tension was terrible. What was it? The fate of the planet may hang in the balance.
No! Annie's got to go!
I'll be right out! For crying out loud!
Gee, almost there. My fingers flew. My mind was a steel trap. Every pore vibrated. It was almost clear. Yes, yes, yes,
Be sure to drink your Ovaltine. Ovaltine? A crummy commercial? Son of a bitch.
So welcome back to Computer Science 50. This is the end of week 2, and that is actually a silly real-world example of what's known as a Caesar cipher. So what Ralphie had there was this Captain Midnight secret decoder ring that, if you look closely, had the letters of the alphabet along one ring and then the numbers 1 through 26 or 0 through 25 on the other one. And based on how you would rotate the thing, it would obviously map different numbers to different letters. And so when he was looking up the numbers and translating them to letters, all he was really doing was figuring out by what key or what value they had rotated the alphabet to come up with that advert. So speaking of advertisements, a few of our own. No new handouts today. The first walkthrough on problem set 1, if you've not yet dived into it or are feeling a bit unclear on it, is now online. Thanks to Kato Uchiyama and Chris Thayer, members of our team. These are being shot this year in HD widescreen, even though we're certainly compressing them to make them more watchable online. But if you pull this up, you'll see something like this. We're going to have to reshoot. Battery. All right, Kato's going to fill in for a moment here.
For this show. Not a show, but walkthrough. I'm one of the system administrators of the course. I'm not a TF or a CA, but I'll be leading these walkthroughs every week on Monday at this time, 6 to 7:30. So, what are these walkthroughs? So this walkthrough is supposed to guide you through the problem set, the standard edition actually. So how many of you have already downloaded and looked at the problem set? Okay, so pretty much all of you? That's good. Okay, and so I'll be going through each of the pages of the problem set, going through each of the problems and seeing what questions you might have, and also guiding you through each of the code sections. So I won't be actually writing the code, unfortunately, but I'll be writing the pseudocode, or I'll be telling you what problems you might encounter in the problem set. So This session is videotaped. It's taped by Chris there. Thank you very much. And it'll be online on CS50.
For filling in there. That was actually not intentional. But these walkthroughs are meant to hold your hand, frankly, if you will, through getting started on the problem set. We'll by default focus on the standard edition of the problem set. These will recur each week, and as the problem sets themselves become more challenging, more time consuming, do avail yourself of these things either in person or online. So office hours. The schedule is online. This too has been enhanced for your viewing pleasure. We have something like 100+ office hours per week spread across the team, so do take a look, and we try to weight them more heavily toward the end of the week when realistically we know you're going to be starting on the problem sets. If you're interested in office hours with me this Friday, lunch with David, so to speak, just drop us that RSVP. And I meant to say something else last time on this note of casualness. You're all very, very sweet to applaud at the end of some of these lectures, but these are just computer science lectures. We don't need to do that, but I'm flattered. Just head for the doors as soon as we're done. Scratch boards, if you do have them in your possession, please get them to a member of the teaching staff and make sure inside the bag is a slip of paper with your name, ID, and username so that we know not to bill you at semester's end. And finally, problem set 2, as if 1 weren't already fun enough, will go out this Friday, and we'll focus on precisely this topic of cryptography. One final announcement from a former head teaching fellow, Thomas Carriero, who's actually at Facebook. He's asked me to announce that this Friday, October 3rd, from noon until 1:30 p.m. in Maxwell Dworkin G135, the ground floor of the computer science building, there will be a Facebook Tech Talk at Harvard. Description: at Facebook, our engineers develop products that millions of people use around the world, work in a fast-paced, high-energy environment, solve tough technological challenges, and interact with equally talented people. So I'm sure you're already familiar with this little startup, but if you're curious in learning more, perhaps getting yourself a job or an internship, do check that out.
Something wrong with the capsule?
No? All right. Oh, God. Not this one.
This is all I got.
All right.
Sorry.
No problem. We're switching to the Britney Spears microphone today. Wow. All right. This lecture. Okay, this is the most awkward thing ever. All right. Whew. All right. So, can't even take myself seriously now. So, where to begin today? So, last time we began to dive a bit deeper into C, and we talked about functions, and we talked about return values, and today we'll start to peel back some of the layers further and talk about what's really going underneath the hood, and also empowering you with some additional techniques that you can do with C. But first, let's try to motivate this as follows. So, I've gone ahead here, and I have connected to nice.fas.harvard.edu using PuTTY, although as you know, you can use Terminal on macOS, Secure CRT on PCs as well. And suppose that my goal very simply here is to write a program that averages the quiz scores for a student in the class. So very reasonable. I already have access to CS50's library, so I can get numbers. But let's see if we can't whip something up here in demo.c. So I'm going to start with this wrote information into argc, although this will soon become clear today what this is all about. I'm going to need to get how many quizzes here. So I'm going to store maybe float quiz 1 score, and then we have 2 quizzes in the course, so I'm going to have at least quiz 2 score. And now I'm going to go ahead and tell the user quiz 1. That's all I need to do there. And now I'm going to need to say quiz 1 gets fill in the blank here. All right, this is getting easy. All right, so get float. All right, then I'm going to do a little copy paste just to speed things along, but all I'm going to do is change the aesthetics there, change the variable there. So now I have 2 floating point values, and if I actually want to print out the, let's say, average of these, I'll say float average gets quiz 1 plus quiz 2 divided by 2. Print, no, right? So order of operations, just like in algebra. So we have to parenthesize that so that it actually divides by 2 the whole sum and not just the quiz 2 variable. Now let's go ahead and print out the average here. So average is going to be, I need a placeholder. So %f, pretty easy. Plug in average here and any bugs, any mistakes that you can see. So I heard a few suggestions, but none of them clearly. argv. Oh, OK. So actually, that's a good point. So that is, in fact, a typo on my part. Turns out it won't matter, because this use of argc and argv is really just convention, but certainly good to adhere to. Anything else? Yeah, so we actually need to include at least one standard library. So include standard IO, because in that library do I get access to printf, so standard input output. It's a very standard function. Anything else? All right, so I also need CS50's library, so let's go ahead and plug that in. Anything else? All right, so not bad. Let's go ahead and try compiling this. So gcc demo.c was the name of the file. Enter. All right, so there's a couple things wrong, it seems. So it's a little cryptic, and it's perhaps more information than I need, but clearly there's something going on at line 12. So demo.c:12 is line 12. And line 14, what was there? Well, it looks like if we look at my blinking cursor, these are precisely the lines where this was used. So what's wrong? Why did I get this? Yeah. Yeah, so when you actually compile this, you have to tell GCC, oh, by the way, those functions that I just kind of took for granted existing in the world, namely getFloat, actually lives in a file called CS50.something. It's somewhere on the system. You don't necessarily need to know where it is. GCC can figure that out based on how we've configured nice for you. But we do need to explicitly tell GCC to link in, so to speak, link, L-I-N-K, in the CS50 library. So -L means give me this library, and then the name of it is CS50. And notice that there's no space in between those two. Go ahead and enter. It seems to compile OK. The name of this program by default is going to be a.out, because I didn't use the -O flag. And incidentally, beware doing something very easy to do but very dangerous to do, like gcc-o demo.c. Very, very bad, because what that's telling the compiler to do is, hey, go ahead and output a file called demo.c. Unfortunately, that file exists and contains your source code. If I were to proceed to hit enter, odds are I'd fill it instead with zeros and ones, or worse, this happened to you, absolutely nothing, if you're nodding your head. So it's an easy mistake to make, honestly. And unfortunately, GCC just does not protect you from yourself. So I'm not trying to pick on you. I've done it as well. So let's not do that, but instead let's go ahead and run a.out. Quiz 1 score, I did really well. I got 100, and I kind of tanked. And it looks like I did OK. And I could now deal with the points of precision by using like something in between the % and the F symbol. But that's not bad. But suppose that we don't actually want to write a program for quizzes, but something that has, say, problem set scores. And there's 9 of those. Well, the natural thing to do, certainly as you're beginning, is, well, first, this is sort of Vim, advanced Vim tricks, but you don't need to know this. OK, now I have a problem set program instead of a quiz program. But I kind of now want to do something like supporting 9 quizzes. So, well, that's pretty easy. I know how to get from 1 to 2. I can just put that in, that in, that in, that in, that in, and then kind of go back here. This has got to become 3. This becomes 3. Oh, looks like I need to change that to problem set. Yeah, it's getting nicer. But very quickly should you kind of cringe at this, right? It's getting clearly very inefficient. It's getting messy. This is very bad style, if not bad design. There's certainly a more intelligent way of doing this. Well, the obvious approach is perhaps to do something like what? So yeah, so use something like a loop. But even then, there's this interesting gotcha where I can absolutely do a loop. And I'll write it in pseudocode for a moment. So in pseudocode, sort of English-like code, I'll say loop from 1 to 9, or 0 to 8, or however you want to define it. And on each iteration, go ahead and call getFloat. And this is actually a good trick, frankly, is you're sort of starting out and you need to sort of make an outline, so to speak, for your code. Just write it out in all English, and then you'll sort of be done with your program, at least on a high level, and can then dive into and actually translate each of these comments to C. Well, my natural inclination, though, might be to do something like this, right? Because we've not yet seen a way where you can, in a loop, create one variable after another. Good? Bad? So bad, if only because what? It certainly looks ugly. It kind of crosses that maybe there's like a smarter way of doing this threshold. But how could we do this? Yeah. Yeah, so we actually need, sort of like we had in Scratch with those things called lists, something to hold multiple items that can ideally even scale to fit them. Well, unfortunately, we don't get quite all the features of Scratch in C. The arrays, or these lists, so to speak, are not going to grow dynamically. You sort of have to manage the memory yourself. But we can, in fact, do much better than this. So let me take a look at array1.c. And what we'll see is this syntax. So at the top of this program, whose purpose in life is just to take in quiz scores and average them, but doing so using a loop, as you already suggested, but also using this new syntax, this bracketed syntax up here. So it seems that I've declared to be of type float, something called grades, but in brackets I've said, give me multiple floats in this case. How many such floats? Well, notice that in all caps is quizzes. It turns out that what C also allows you to do at the top of your file is by way of these preprocessor directives, a fancy way of saying anything that starts with a sharp sign, like include, go ahead and define a sort of constant, so to speak, called quizzes to be the hard-coded value 2. And what this is going to ultimately do for us is with this one line of code here that I've highlighted is create not one, but 2 floats for us. And in fact, if I realize, damn, we changed the structure of the course and next year there's going to be 8 or 7 quizzes, well, all I have to do now is recompile the program, and assuming everything I wrote is correct syntactically, now it will just work for 7 quizzes instead of 2 because I've sort of dynamically defined this thing. So what's going on? So in C, you have this ability to define what are called arrays. So this is a picture taken from one of the tutorials we recommend online. So this is howstuffsworks.com, and it's part of the C tutorial that we have a link to on the first problem set. This blue box here is just depicting a computer's memory. And at top left here, where you have the variable b, this is just, like I've done before, depicting with a square a chunk of memory, namely how many bits? 32 bits, or 4 bytes, remember, was the default size for an integer. And this is, in fact, an int, though smallly written up there. So b is apparently an int. We'll represent it with just one square, apparently stored in this chunk of memory inside of your whole computer's RAM, represented in blue, is just the value 5. But by contrast, if we do something syntactically like this, so at top right it says int space a, and then in brackets the number 4, followed by a semicolon, that's equivalent in spirit to saying something like int a semicolon, int b semicolon, int c semicolon, int d semicolon. You're just getting 4 of them, but the nice thing is that they're all, you can refer to all of them by way of the same name and then an index value, so to speak, like their location in this chunk of memory. So when you declare an array in C, so to speak, you get not just one chunk of memory per se, but as many as you actually want. And one of the neat things about arrays in C is that they're contiguous in memory, which actually is a good thing because it makes it easier to get at the memory you care about, but it also makes it very dangerous and makes us vulnerable to those things called buffer overflow exploits. For instance, the thing that took over the iPhone last year when CS50 actually was just beginning. So when you declare a variable like this using square brackets after the name of it, you get an array, and you get as many of those items, those data types, as you've specified numerically. So what does this mean? Well, first, let's go back here. And just to be clear, if quizzes equals 2, as in the case of this fall semester, what this line here is equivalent to is saying give me 2 floats called grades, and ultimately I'm going to access them individually by way of grades bracket 0 for the 0th element, grades bracket 1, and if then I try to access grades bracket 2, bad things tend to happen because you're going farther than the boundaries of your own memory. So let's see how this thing works. So quickly let's run make array1. All right, seems to compile OK. Let's go ahead and run now array1. What were your quiz scores? All right, same as before. 100, and it tanked to 50. Seems to work. Your average is 75. Now, suppose we roll back to last semester, which, for better or for worse, we had actually 3 quizzes. All right, so let's go up here, change this, so we can roll back time. I saved it. I'm going to recompile it with make, but that's the only change. Now I'm going to rerun array1. Now notice it automatically says quiz 1 of 3. So I got 100, I got a 50, and then it didn't show up. I got a 50. All right, so the program scales. But there's still kind of a downside here. Right? It's definitely easy now to make the program capable of more scores, but arguably what's a downside of this approach? you have to recompile. So going through the process of finding your source code, finding a system on which you still have an account so you can compile it, and then actually compiling the code after making some trivial change doesn't feel like the most efficient process. It's certainly not the best software that you could put together, because it certainly doesn't sort of lend itself to being adopted by more people than just you if they just simply have different numbers of quizzes each semester. So there is a way where we can have more dynamism, and we can even ask the user when he runs the program, how many quizzes do you want to input the scores for? But we can't do that quite yet, and we'll start doing that next week when we start getting into dynamic memory allocation. And in fact, and by that I mean asking the computer, the operating system, for more and more RAM if and when you want it, rather than having to predict in advance by hard coding how much you want in your program. So this picture we put up on Monday saying this represents your computer's memory, and at the bottom there's this thing called a stack, and just like in a cafeteria where you grab a tray, and you put, or rather when they've finished cleaning the trays and they put them back, you stack one on top of the other, on top of the other, on top of the other, just like main gets called first, then main calls maybe printf, then printf calls something else. In short, every time a function gets called, it gets its own chunk of memory called the stack frame on top of this part of RAM called the stack. But it turns out there's another type of memory that you, the programmer, have access to, and it's literally on the other side of your computer's RAM, so to speak. It's at the top. And every time you ask the operating system, starting next week, give me more RAM because the user wants to input more quizzes, or give me more RAM because I need to try to crack more passwords and this necessitates more memory, well, unfortunately, the memory you ask for is going to sort of creep lower and lower and lower pictorially in your computer's RAM, while meanwhile, when you call more and more functions, they are literally growing up and up and up and up. And if you're thinking this is kind of a bad idea, well, it kind of is, because you can create situations in which they clobber each other, and then more bad stuff, we'll call it for now, happens as well. Now, fortunately, these days, this box is how big? How much RAM does every program you run on a typical computer have the illusion of having access to, even though it'd be rather insane for most programs to need it? So not your entire hard drive, but more properly your entire bank of RAM, so random access memory. And even then, that's not quite true, because most operating systems put a limit on it. If you're running Windows XP, for instance, even if you've got 4 gigabytes of RAM in your computer, every program you run, even Photoshop, which arguably does need and want lots of RAM, can only, by nature of how Microsoft designed XP, use 2 gigabytes total. And it was just sort of a hard-coded value, but it does have to do with the fact that computers are 32-bit computers, and what's the biggest number you can represent with 32? All right, so 4 billion, so that's like 4 gigabytes. Well, it turns out Microsoft sort of decided, you know what, we want maximally 2 gigabytes of RAM for the operating system. We'll let the user's program have up to 2 gigabytes. 2 plus 2 is 4, and that's as much RAM as you can have in Windows XP. Vista and other operating systems sort of pushed past that 4 gigabyte limit. But anyhow, a sneak preview of some of the sort of more low-level details that are to come, but they hint at how you can induce intentionally bad things to happen. If, for instance, you're trying to compromise a system and you know, well, if I feed more and more data into this computer, that stack is going to grow up and up and up and up, or that heap is going to grow down and down and down and down. And so just to give you a teaser as to how these security compromises tend to go down, usually the type of input a user is providing to a web server or to a program when they're trying to crack it or break it is zeros and ones that represent malicious code. So code they wrote, compiled, grabbed those bits, and now we're trying to feed it into another program, because if you sort of clobber important parts of the stack, you'll actually trick many computers into running the code that you sort of pushed in as though it were user input. So in short, this tends to happen because people screw up when it comes to using arrays. Because notice again, how big is the array called A here? So it's of size 4, it seems, right? It was declared to be of size 4 in brackets, and the 4 square boxes here suggest that's of size 4. But it turns out if you try to access A bracket 4, or A bracket 5, or maybe better, A bracket 1000, what memory are you going to be accessing? So, like, who knows? And therein sort of lies the danger. It could be some other program or even the operating systems that you're not supposed to have access to. Well, notice how we've implemented this now. So let's come back to the actual code. So on this line here, there's another trick that we can introduce here. If you know you want to declare multiple variables of the same type, you just separate them by commas, whether they're arrays or singletons, like in the case of grades is an array, sum is just going to be the summation, but it's just a single variable like before. I need two ints though, I decided. I called them average and I. I could go ahead and declare them lower in the program, but I wanted to emphasize the variable, so I left them at top, which is fine. So then we asked, what were your quiz scores of the user? This loop is pretty much what you suggested. Come up with a loop and just iteratively call getFloat. But how do you plug those values into the array? Well, you do something quite simply like this. So grades, bracket, where do you want to put it? Gets whatever number you want to put there. And then down here, I have initialized sum to 0. I have another loop, which maybe already hints to the more astute, well, maybe I could have done this all at once and saved some time. And yes, that is in fact true here. So I've got another for loop here. It's iterating over all of the quizzes from 0 up to this value, which again we said is 2. And then what's this line of code doing here that's highlighted in white? Yeah, it's just adding the current quiz, the ith grade, so to speak, to the current summation again and again. So this syntax, again, to be clear, is the same as saying sum gets the current sum plus the ith grade. But it's just a neat little syntactic sugar, so to speak. So what does this line do? Yeah, so it takes the average, but in kind of a neat way. So what happens if I take sum divided by quizzes and then cast it to an int? Yeah, so it floors the value. It truncates the value. So if I've got some value like a quiz score of, 11, let's just say, and a quiz score of 10, right? There's two such quizzes. Average those together, I get 10.5. You, the student, probably, but like pathetic though that score might be on a scale of 100, would probably rather have the 11 than the 10. But if we just take sum divided by quizzes, cast it to an int, what are we going to give you? Right, a 10, because when you cast, you sort of cram into the variable only the stuff that will fit, and in the case of a float being crammed into an int, you lose everything after the decimal point, and so the student gets a 10. So if we want to round, and we don't have like a built-in round function, well, it turns out that you can implement. You can sort of roll your own round function by just adding to whatever floating point value you have, 0.5, because that has the effect, no matter what the resulting math is, of rounding up. So in that case, if we do 11 divided by 10, or rather the average of 11 and 10, that gives us 10.5. Add in a 0.5, that gives us 11. Cast that to an int, and we get 11. Meanwhile, though, suppose that your scores were 10 and 10 and 10 and 11. So your score is something like 10.2-ish. Well, add in is that going to work there? Yes. Add in, if your average at that point is 10.2, add in 0.5, that gives you 10.7. So you don't cross the 11.0 threshold. And so when you cast it to an int, your average goes down to a 10, which is what it should be. So that's all fine and good. It's kind of a neat trick. You can implement round, which wasn't all that hard to think about in the first place. But thankfully, there are sort of people in the world who have done this kind of minutia for you. So array2.c, the second example, which is in, again, Monday's handout, is identical except for this last line here. So what have I replaced my 0.5 trick with? It looks like I've replaced it with another function. This little mini program that takes input, in this case produces output, and it's doing that math for me. But where did it come from? And how did I know this existed? Well, let's scroll up, see if, so there's this other library. And by including, it turns out, the header file called math.h, I get access to things like round and other such mathematically oriented functions, but there's a catch. So it's not hard to imagine how this thing works. So let's just go ahead and assume that it is going to work as expected. So GCC of array2.c. First problem here, though, get float. So I have to do my same solution as before, dash LCS50. That gets rid of one of the problems, but there's still another. Now it's complaining about what? So undefined reference to round. So this is actually what's called the linker complaining at you. And we'll come back to this way later in the course. But this is a part of the compilation process that's trying to take your code, your, in this case, array2.c, all of the zeros and ones that are produced as object code, and it's trying to find the zeros and ones that represent the round function, but you didn't implement them. They're somewhere else on the system, but the linker doesn't know where to find them unless you tell it to, so to speak, link in the math library. And again, in this spirit of Unix people being very succinct, the math library's nickname is M. And so you do -lm as well. And it's unfortunately wrapping onto 2 lines here, but it's just gcc array2.c -lcs50 -lm, and everything seems to check out. If I run array2, if I run a.out, because I didn't specify the file name, 100, 90, and this time I get 95, which is also to be expected. But there is a trick. If you're sort of if you very easily forget what all the little minutia there is, or if, frankly, it just gets very, very tedious to type again and again, what's the trick? You can just say make array2, and notice the lines that are outputted automatically include not only at far right -lm and -lcs50, but also some other stuff. And that's because we don't have full access to nice.fas. It's run by FAS itself. We've installed, apparently in this directory, this path, a whole bunch of stuff for students in the course, and we've just configured your environments, your shells, in such a way that all those flags just get inserted automatically, or automagically, if you will. All right, so any questions about what an array is? Well, what was happening there, to be clear? So if I declared this thing called float grades, and just to be explicit, 2, all right, what actually happened? I got some chunk of memory somewhere in my computer's RAM. That thing is called grades, so we'll just label it as such. This is going to be index location 0. This is going to be index location 1. So if I call grades bracket 0 gets get float, and the user types in 100. Well, what happened? Literally, the user types in 100, it gets stored in this chunk of memory here. The user types in 90, it gets stored in this chunk of memory here. Meanwhile, that variable called average, well, that was just one int, not in an array. And so what ended up in there was 95, and that's the same sort of boring story from last week when we first introduced variables. So that's all there is to arrays. But they're implemented using various memory tricks that we'll see next week allow you to do some very bad things. In fact, let's take a look at one such mistake. So here we have a program called Buggy6. It looks almost the same, but there's a bug in here somewhere. So that's all the code. Even without running this, what's the problem? Oh, I kind of heard it. Speak up a little. Yeah, so the second for loop, for some reason, and then I can actually kind of guess how this happened, has what you would goofily call a magic number, which is just a fluffy way of saying it's a constant value you hard-coded, probably as a bad idea. The reason being, probably at some point when I first wrote this program, we had 3 quizzes, and so I hard-coded in a loop going from 0 to 3, another loop going from 0 to 3. Then I realized maybe we should actually abstract away how many quizzes there are with this thing called a constant. So I defined quizzes. I substituted in the previous value of 3 there, but then just completely forgot, perhaps, that it would also belong there. But more interesting, besides the sort of mistake that it was, what if I run Buggy6? After compiling, let's see what actually happened. So Buggy6. What were your quiz scores? 100? 90? Oh, stupid tablet is covering this number. Apparently got 0. So what just happened? I iterated 3 times, but I only inputted 2 values. Let's try again. So 50, 60, and then 0. So what appears to be stored at the location called grades bracket 2. If I'm counting correctly. So apparently 0.0. Well, this is kind of neat. I don't even own that memory. Why don't we see what's location 4? So I'm just going to change the loop to go from 0 to 4 instead of 0 to 3. I'm going to go ahead and recompile. And then I'm going to rerun Buggy6. I still am only being prompted for 2 scores, and that's good, because otherwise this would get tedious to type. Ooh, that's interesting. So it looks like, what, 8 bytes away from, or 4 bytes away from the location I do own, there's someone else's memory entirely. So specifically, I declared an array of size 2 using that constant called quizzes. But what we've just discovered is that down here, physically in RAM, is apparently the number 0.0. Then further down in memory, another 4 bytes later, is negative 1.52. All right, so this is kind of neat, because now you can start poking around gigabytes worth of memory, it would seem. So let's take a look. And frankly, this is what hackers do. This is what they try to do to induce programs to behave in ways the programmer did not intend. So now I'm going up to 14. Let's see what happens here. Quiz score of 100, quiz score of 50. Interesting. So that's kind of a pattern. So it appears that in RAM, somewhat recently, was maybe some kind of repeating pattern. Maybe this is a coincidence, but it's a little suspicious that it's the same values. Let's get a little braver. So how about location 100? So 400 bytes away from the start of this array. Let's recompile, rerun it. And notice the numbers I'm typing in at the beginning don't seem to be affecting anything, because they are ending up in legitimate places. Well, that's interesting. So there's just some big chunk of memory, it seems, that's been initialized to some pattern of bits. Let's go further. Another factor of 10. Recompile, rerun, 150. OK, so now we're back in the realm of zeros. All right, that's still nothing. That's 1,000 bytes. That's like 1 kilobyte. Let's really push the envelope. How about there? So that puts us into the range of a megabyte. No, not even. A megabyte into the memory. All right, 150. Ooh, and now we broke it. So it's maybe overwhelmed by all the crazy numbers there, but notice the last line. Segmentation fault, core dumped. Might seem a little silly, but mark our words, this will happen to each and every one of you multiple times during the semester. What this means is that we overstep the boundaries of our segment of memory. It might mean that maybe the heap and stack collided, but not probably in this case. But it means that we try to access memory that not only did we not own, but we really didn't own it. And the operating system finally clamped down and said, you were going way too far into the memory space. That's it, dumping core. What does that mean? Well, it means if I do an ls, there appears to be a file in my directory called core. If I do ls-l per the problem set, that shows you file sizes. That appears to be a decently sized file, 300,000 bytes. And what that represents is what, do you think? What would be useful maybe for the operating system to spit out in the event you screwed up with respect to memory? Yeah. Yeah, the memory in question. So what a core dump contains, among other things, is sort of a snapshot of what was going on in memory at the time your program or you screwed up. Clearly not all of it, because it's not 2 gigabytes worth. But then again, I wasn't trying to use 2 gigabytes worth of memory, so I don't really need to get a file of that size. But if you start poking around in your own account, and we see every time CS50 submit is run, a couple core files sometimes slip in, and it's, oops, something went wrong there. They can be useful, and we'll see probably starting next week that you can use tools. One tool called GDB, the GNU debugger, to actually look inside that file and poke around as to what went wrong and where. But for now, let's just assume it's a bad thing. Well, it turns out that we've been using arrays for a little while already. So this is another example called string1.c. It's very short, but it uses another function from CS50's library called getString, which up until now we've just been treating as the conceptual entity of a string, like a bunch of characters concatenated together, like an English word, English sentence, whatever. But it turns out that we can actually treat strings as though they were arrays. Because even though we think of them as just one entity, let me spin this around for some blank space. What a string really is, actually, if you were implementing a string and you know what other primitive data types exist in C, what data types would you use to implement the string? You've got chars, right? You've got a character, so why not treat arrays, or rather, why not treat strings as just sequences of chars, aka, according to today, arrays of characters. So when you say something like string S gets quote-unquote foo, or equivalently the user types in foo upon your calling getString, sort of the same effect. What's really happening in memory is that there's not just one piece of memory a la an int or float that you're then cramming the word foo into. What's rather happening is that there's a bunch of memory, contiguous, that is back to back, inside of which is going F, O, O, but then something else. Because if all your RAM is a whole bunch of bytes back to back to back to back, and your computer actually needs to tease apart what's a string, what's a float, what's an int, what's another piece of data altogether, you kind of need to demark the end of something interesting. Because a string is not fixed at 32 bits or 64 bits. It can be any length, just like an English word or sentence or paragraph or entire document. So strings are sort of special in that they get this terminal value at the end of them, the null character. So \0 means it's not the number 0 per se, but it's all 0 bits at the end. And why do you think it would be useful if after every word that you have in memory, or every string rather that you have in memory, there's this special value at the end, this null character, so to speak? Why is that useful? Yeah. Yeah, so it delimits 2 separate strings. Unfortunately, it comes at a cost of a byte. Like you spend 8 bits to actually store a character in ASCII here. It's the special character that's all zeros. But it means if I then have another word following this, I can actually have the word, say, 1, 2, 3, 4, BAR \0. Because if the user also did something like string T gets quote unquote bar, that too has to go somewhere in memory. So who cares? Why does this come into play? And who actually looks at this information? We'll take a look at this example here. So in this example here, we're calling getString. Then I'm doing this crazy thing, which we'll tease apart in a second, saying if S is not equal to null. Well, you can kind of infer what this is doing. It's probably some kind of sanity check saying if the user actually typed something in, go ahead and do the following. Well, what does this loop appear to be doing? That loop in the middle. Yeah, so it's just iterating over the characters because it turns out there's this other function called strlen. Again, it's very succinct, string length, that takes an argument of a string, or more properly, an array of characters. And what this is having the effect of doing is iterating from 0 on up to the length of that string. And on every iteration, what is this line of code doing? C gets S bracket I. It's storing in C just the ith character from that string. That is the ith character from this array. So if I is initialized to 0 and you do S bracket 0, what letter are you going to get back and tuck away in the variable called C? The letter F. You then increment 1 space, so I equals 1, and now we have O, another O. But we're not going to hit this point because what would you hope strlen returns when past the word foo, as represented here? So it does return what you would hope is the length 3, FOO, and not 4, which would just get confusing, if nothing else. So it uses that special sentinel value, the \0, the null character, so to speak, but you do not have to per se. So the effect of this program is, this is string 1, so make string 1. Then let's go ahead and run string 1. Type in the word foo. It just prints 1 character per line. Not terribly interesting. David, same thing. What if I try to get fancy and I hit nothing and I just hit enter? Well, that seems to be OK, because it turns out we try to sort of protect you from yourselves. So CS50's library in getString, we check if the user just hit the enter key, what does it seem that we're returning only? So we're just returning to you that. So it's the empty string, so to speak. It's a string of length 0, but unfortunately to represent that trivial idea, we have to spend a byte and actually return that. But there is one way to break this potentially. So it turns out with many programs, you can break out of them per problem set 1 by hitting what keystroke? So Control C. So the next time you screw up and have an infinite loop, Control C is your friend, or like the little X in the top of the corner of the window. But if you actually want to induce the idea of end of file, so to speak, that is, you want to tell the program, I got nothing for you, not even a carriage return, not even a strike of the enter key, you can hit Control D, and that has the effect of feeding nothing to the program. But what does getString probably return then? Well, in that case, when your program is fed literally nothing, aka Control D, if you want to simulate it manually, it's apparently passed null. And let's see if I can break this. So let's delete this, because that was checking for null being returned. Now I'm just going to make a leap of faith, and if I really want to be anal, I'll reformat this. Okay, now it's as though we're never there. I'm going to remake string 1. I'm going to rerun string 1. I'm going to hit enter first. And that's OK, because it still handles it, because it returns that thing. If I hit Control D, bad things happen. Hypothesize what bad thing just happened. So I returned null. And then what did I do with find its ith character, or rather, no, even before. Function. If you pass it a legit string that's some number of characters, even 0 followed by \0, aka null, that's good. It can deal with that. If you pass it literally null, that is nothing, it freaks out. And it tries to sort of touch memory, the null, literally memory location 0 in your computer's RAM, which is sort of special cased by your operating system to be off limits to everyone. The very bottom left byte of memory, so to speak, in the picture is off limits. And so it dumps core because it's trying to touch memory that doesn't belong to you. And we'll spend more time on this when we talk about pointers. But that bug alone sort of hints at, again, both the power, or at least how close we are to the hardware, but also the kinds of bad things that can happen. And again, it's these kinds of stupid mistakes that explain many systems compromise these days. So here's a slightly different version, and I say in the comments atop this file, string2.c, that it's slightly optimized. What do I appear to be doing differently, which is arguably better design insofar as it's smarter, it's more efficient? So I've got an extra variable, looks like it's called n. I defined it up here, which is fine, although again, for the newer version of C, I could have defined it in here too, but I'm now initializing it to be what? The return value of strlen of s, and then what's my condition? Well, same idea, but instead of saying I is less than strlen of s, which to be clear is what I did last time, notice that my condition was I is less than strlen of s. Why might I have gone through the trouble to rewrite this whole program to instead introduce a second variable, which is arguably itself sort of unnecessary, because clearly it's possible to get the job done without, but to do this? Yeah. Yeah, so this is better design in as much as the condition of any loop, recall by nature of a loop, is checked again and again and again and again. And so in this first version, how many times do I call strlen of s if the word s is foo? Right? So 3 or actually takes 4 times, because on the 4th time do I realize, oh, it's not as long as I is now, and so I'm going to terminate. But what's sort of stupid, literally, about that? It's the same string, right? This is a very deterministic process. If you ask me, what's the length of foo? I'm going to say 3. 10 microseconds later, you say, what's the length of foo? It's still 3. You ask me again on the next iteration, still 3, still 3. It's inefficient by nature. And any time you're doing this, you're just wasting CPU cycles. You're literally wasting the user's time. And so this version, where I actually have a second variable, it's doing what for me? It's checking this length once, and then just comparing the value of I against n. Now, nothing is free when it comes to coding and in general computer science. So what am I spending in order to get this time benefit, this performance increase? So space, which here's pretty silly, right? You might as well spend the extra 32 bits and avoid doing something stupid, because if you input a string that's not foo or bar, but say one of Shakespeare's plays as the string, you literally paste it in. The program should be able to handle it, but you probably don't want to be checking the length of it again and again and again. Because how do you think strlen checks the length of a string, which again is just an array? How would you do it? Start at the beginning, check, check, check. Aha, the special character called null, the length was 3, because I took 3 steps to get there. So that's literally all strlen does. It's a loop, but for performance reasons back in the day, they said it's up to the user, the caller, to actually check if the string is there or not. We're just going to assume that it is. But assumptions, again, tend to be a bad thing. So any questions on arrays or some of these tricks. All right, so let's tie this together to this notion of casting that we did the other day. So in capitalize.c, similarly a simple program, but we're tying together some of the syntax of last time on this. So this program seems to get a string, and then the purpose of this program is, I'll spoil it, as its file name already did, to capitalize whatever you type in. So that means if I run, first of all, capitalize, if I compile it, if I then run capitalize, and then I type in foo, I get back foo in all caps. If I type in David all lowercase, I get David in all uppercase. If I type my name properly, still goes to uppercase. In short, this program capitalizes, but what about this? The quick brown fox ... So it seems to handle that OK too. So it handles punctuation, it handles spaces, and only appears to capitalize legitimate letters. So how does this work? Well, we've got this loop, which I seem to have stolen from the previous example. This loop is going to iterate, as you can probably see, over the string. So nothing too magical there. But what's this branch doing in here, these two conditions? So in English, someone proposed how to translate this line from C into English. Yeah? Or is that a stretch? Oh. OK. Perfect. Perfect. So to recap, the first line there that I've highlighted in white, if the ith character of S is greater than or equal to A, and that same character is less than or equal to Z. Now I'm making an assumption that A to Z are numerically sort of contiguous, but we know that from the chart. We know that little a is, what, 97, and then little z is 26 past that, with everything else between one step away. So if we find that the ith character in S is, that is to say, lowercase, we're going to print it out, or print out a character. What are we going to print out? Well, it appears that we're going to print out the ith character itself minus this craziness. Why does this work? Yeah, so it casts these characters to numbers, figures out the offset between lowercase and uppercase, because I just forgot when I wrote this, right? Now that I think of it, if capital A is 65 and little a is, what, 97, that's a difference of 32. So really, I could have just taken a lowercase letter and subtracted what to get uppercase? 32. I didn't remember that, and what better way to re-demonstrate casting by saying, well, let's let the computer figure it out, albeit at someone's expense. So little a, which is bigger, minus big A, which is smaller, subtract that from the actual character, and this has the effect of forcing it to uppercase. But how do we deal with punctuation and everything else? We just print it through raw, whatever it actually was. So this is kind of neat. You know, silly example, but it kind of ties in a lot of these different things. The branches, the arrays, the stir length, and actually the format strings and casting. It's kind of everything, except for that there. OK. So where can you go when you have to look these kinds of things up? So for instance, the place that we point you to in the problem set is the man page, the manual pages, so to speak. So for instance, this thing called round. If I looked up, actually let's start with printf, man printf. This brings up the man page, so to speak, for printf. But what you have to be careful of is that sometimes on Linux and Unix there are commands that are identically named to C functions. So it turns out there are different chapters in this manual. And generally, chapters 2 and 3 are the ones you care about. So if I go ahead and type man2 for chapter 2 printf, nothing's in chapter 2, it seems. Man 3 print. Aha. There we go. So notice the difference. And again, this is to point this out now so you don't waste time in the lab banging your head against the wall wondering why the documentation isn't what you expect. In top left, it says printf, chapter 3. When I just typed man printf, I got chapter 1, which is actually a command that you type at your prompt. It's not a C function. And it should become obvious because, look, nowhere here is there mentioned any header files, any libraries. But by contrast, man 3 printf, there's something familiar. So some of this will still look a little cryptic until we start teasing these things apart. And sometimes the people who wrote these functions decided to document it and a whole bunch of other functions all together. So apparently printf is related to things called fprintf, sprintf, snprintf, and a whole bunch of other things. We'll see a few of those later in the term. But for the most part, you can kind of skim to get a sense of what's in here. And generally, you'll care about what the return value is. And you might want to read the sentence or paragraph describing what the function returns so that you know how to deal with its return values. Sometimes you want to look at the format strings or what you're passing in, the arguments. So in short, if you sort of read this stuff, that's sort of the definitive documentation, though a little more user-friendly than that are places like this. So I would say the best free resource that at least I rely on out there is this guy, cppreference.com. So it is C++, but that's effectively a superset of C, which we're doing. So the interesting stuff for us is pretty much everything here in the left-hand column, despite its mention of C++. In particular, standard CIO. That sounds vaguely relevant. Let's click this. If I now scroll down, it looks like there's a whole bunch of functions here. Here's one that's a little more familiar sounding. And what I think you'll find is that this documentation is much more user-friendly than the documentation written 10, 20 years ago in the man page environment. You sometimes even see examples, as in this case. Well, what about round? Well, round, let's try that. So man 3 round. OK, I guessed right. Chapter 3. It looks like it's in the library called math.h. And it looks like this is its usage. So it turns out you can sometimes have functions that are called one thing but do different things depending on what data types you pass them, depending on different parameters. So it turns out you can pass this function called round a double, but you can pass something similarly named roundf, a float. You can pass roundl, a long double, which is like a even bigger double on some platforms. But for the most part, we probably only care about this. In fact, for some of you, for the greedy program, you might care about using this one. Why is this useful? Well, if we scroll down, oh, and notice it even told us. So if we ever say RTFM, we mean go pull up the man page and look for something like this. It's telling you exactly how you should link, what flag you should use after GCC. So notice, what does this return? The rounded integer value. If x is integral or infinite, x itself is returned. So that's useful to know so that you can expect the behavior per how it's defined. And then here, looks like standard C math. Looks like, wow, so there's a bunch of things, logs and sines and cosines, including round must be elsewhere in the manual. And oh, that's strange, actually. Oh, we'll look that up later. OK, any questions on libraries? And the first of those links is more of a tutorial on C and more. So we've seen this stuff before. And let's actually tie this now together to crypto. So we've seen arrays before. Up until now, every time you've implemented a main function, odds are you've literally typed something like this. Well, it turns out that programs that you write in C by default can take arguments, so to speak, not parenthetically, not only parenthetically, but literally at the command line. So when you run GCC, GCC takes what are called command line arguments, the name of the file you want to compile, a switch like -o, a switch like -l, CS50. So you can control the behavior of programs by writing extra words after their names on the command line. So how do you write a program then that itself takes such input? Well, you finally start using the stuff you've been typing verbatim without actually using this. So it turns out that main, which again is this function that's called by default, always takes, or can always take, two arguments. One is called argc, which itself is just the number of arguments passed to your program. And one is called argv, and it's apparently an array, aka vector, although they have slightly different meanings. There's argv, argument vector. That's the etymology of it. But apparently, it's not an array of strings. It's an array of char stars. Well, it turns out one of the little white lies we've been telling, and we'll continue to tell a little longer, is that this is the file called CS50.h. So the URL for this is in today's slides and Monday's slides. But this is a file that we won't spend time on until next week. But if I scroll down, notice that in this file, have we taken it upon ourselves to say, we are going to create our own data type for string variables. We're using this keyword called typedef. And apparently, we are making the word in blue, string, synonymous with char star. So it turns out that a string is clearly related to chars. The star suggests that it's actually related to arrays because stars imply pointers. Pointers mean memory. And clearly there's something about memory when it comes to arrays. And we'll spend more time on that next week. But let's take a look at how we can actually use this. So argv1 is the first such example. And this will be useful for problem set 2, where you actually, too, have to take this kind of input from the user. So if I run argv1, it just seems to do this. But if I run argv-foo, it seems to print itself and that first argument. Argv-foo bar, argv-foo bat, it's kind of a pattern. So how is my program getting at what I have typed literally at the command line? Well, let's take a look. So in argv1, which again is among your printouts for reference, it's a pretty simple program. So I'm first, just to be anal, printing a new line. And the last thing I do is print a new line, again, just to make it clear what's being printed. And then there's just this loop. So I'm iterating from I equals 0 up to argc, which is the argument count. How many things were typed literally at the command line, how many words. Then I'm printing a string, %s a string, a new line. And then the ith argument. So it turns out that in argv, which is just an array, is not individual characters in this case, but individual strings, which we'll see next week is in turn an array of characters. So argv is actually like an array of arrays because it's an array of strings. Or it's kind of a two-dimensional grid if you start thinking about how you would implement an array of arrays. But we don't need to worry about that now. But what if I want to do something a little more interesting? Make argv2, which we'll see is a little fancier. argv2 apparently prints one character per line. Foo, bar. So it seems not only can I iterate over each word in argv, I can apparently dive in deeper and within each word iterate over its characters. Well, herein lies that use of arrays. So it's slightly longer, only because we have a nested for loop. But take a look here. We've got, again, printing a new line, iterate over all of the arguments, same as before. But then inside of that for loop, what is this highlighted line doing? In English. Yeah, iterate over each character in the current string. Well, what's the current string? Well, it's the ith word from the prompt. What's that? Well, that's argv of I, right? Because if there are argc words at the prompt and we're iterating from I equals 0 up to argc, well, then argv bracket I will give us the ith word from the prompt. But now I care about what is its length. So if I just pass to Sterling that string called argv bracket I, using a different variable, say j arbitrarily, how do I print the jth character of the ith word? Well, turns out you can nicely stack things like this, like two-dimensional arrays. argv bracket I gives me the ith word in argv, ith word I typed at the prompt. Dive in deeper with another set of square brackets, I get the jth character. And if you really want to get crazy and like to think in 3, 4, 5, 6 dimensions, you can do it, but you start to spend a lot of memory because everything's got to fit somehow into RAM. But the point is that our programs can finally take input, which will be useful if, for instance, you're trying to encrypt something at the command line or implementing your own program. So this was just to recap and allude to the fact that all of these functions and those data types are in CS50's library, but there are some bugs, and they're intentional bugs. And the astute among you might take a look and realize that when we're asking the computer for the operating system for RAM, for memory in these programs to fit arbitrarily large strings that a user might type, our library actually never gives back that memory. And so this danger I alluded to earlier, where you ask the computer for memory and then never give it back, the effect of which on your own personal computers is often to slow the thing down to a crawl, ultimately, well, we're just as guilty of, though we intended to do it in this case. So cryptography. This is, be sure to drink your Ovaltine. And why? What was the key? What was the secret that allowed us to decrypt this string? It was 13, ROT 13. So in general, cryptography is the art of concealing information, encrypting information so that what is viewable to humans as plain text is no longer viewable to them as easily as ciphertext. And generally, cryptography comes in the form of something that requires a secret. So secret key cryptography is the use of, is the art of scrambling information by using some secret value that only the sender and the receiver ideally know about. And in the case of little Ralphie and little Orphan Annie, and even this example here, well, we called this thing a Caesar cipher last time. Actually, we'll come back to that in a second, but it relies on the secrecy of a key. Or in the case of Ralphie, it required that he own that Captain Midnight secret decoder ring. So that was sort of the secret. You had to shell out some number of serial box tops in that particular context. But the key doesn't have to be a number. It doesn't have to be a stupid little device. It can actually be something arguably more complicated. So World War II, the Germans actually used this thing known as an Enigma machine. It looks pretty much like a typewriter, but inside of that thing were a whole bunch of gears and levers that had the effect of creating a box that you can rather literally think of as a black box, where if you type something at the keyboard as input, it produces output as a result of rotating and turning all of the hardware inside. And it was all configured in such a way that only the German engineers knew how it was defined, so that if the Americans or anyone else intercepted a message that had been translated with this device from plain text to some scrambled ciphertext, the only way the interceptors, say the Americans, could decode the message was to do what? Right, so you could brute force it, so to speak, try all possible combinations that map the English alphabet or the German alphabet to the German alphabet. Right? Or you can maybe make some assumptions. Let's do a statistical analysis. Maybe the letter A is just as common in German as it is in English, so let's look for the most frequently occurring sort of scrambled character and just take a guess that it's A and try to chip it away at it that way. Or you can take the other approach, which, I mean, the military did, in addition to that, presumably. Right, go after the German U-boats and try to actually steal the device. And in fact, every year, fewer and fewer people seem to have seen this movie, despite Matthew McConaughey's fame. U-571, have you ever seen this movie? So the whole movie is, I think, okay, two of us have seen this movie. Matthew McConaughey tried, three of us, jumping on German U-boats, trying to steal their Enigma machine, because the key to cracking the German ciphers was to physically have this device. It was a lot easier, arguably, to steal the original device than to figure out in a vacuum exactly how it worked. So this Enigma machine and ROT13, the little Ralphie thing, is an example of what's generally called secret or symmetric key cryptography. And it's symmetric in the sense that for it to work, both the sender and the receiver have to have the same information. That's secret. And so generally, you've got some plain text. You run it through a cipher, an algorithm, a function that uses a key, so to speak, a number in one case, a machine in another, to produce something called ciphertext. And then you use that same key or that same machine to decrypt the process. So therein lies the symmetry as well. So the Caesar cipher is one of the earliest examples of this. If you read up on this on Wikipedia, this is one of those age-old stories where apparently Caesar used to encrypt messages to his generals by literally taking his message on plain text, rotating the letters a few places, and then sending some brave courier with the ciphertext across the battlefield so that the general on the other side could then subtract 13, for instance, from every letter. I mean, it's named a Caesar cipher because this is supposedly what they used. And arguably, this was not a very sophisticated technological culture back then, so perhaps it was sufficient to rotate things by 13 places, but the world has certainly progressed beyond that. For our purposes, though, it's nice because it's a deterministic algorithm. Input produces output predictably because we can formalize the Caesar cipher like this. So at the top there, this is just a formal, succinct way of saying that the ith letter in the ciphertext, C, is simply the result of taking the ith character in the plain text, adding some number k, like 13, and then taking the sum mod 26, where 26 in this case is obviously the size of your alphabet. And you could use other alphabets, certainly, but so long as you agree upon a standard, like the English alphabet, we would use a modulo of 26. And this picture just depicts a shifting of what? A key of what here? It's a key of 3, it seems, right? A becomes D, B becomes E, and so forth. It shifted 3 instead of 13. But Caesar, not so good. Why? And clearly there's better. But Caesar, not so smart. Why? Right? If you only have 26 keys, right, even the slowest of couriers who intercepts the other courier could kind of pause for a moment, try all 26 letters of, say, the English alphabet, and take a look at what pops out. And the sentence that actually looks like English, in our case, is probably the one that Caesar was trying to send to someone else. It doesn't take that long to brute force the algorithm. There's other problems, but let's just improve marginally. So the French, arguably, years ago, had a more sophisticated cipher. The Visionaire Cipher is the same idea, rotation-based, but instead of just using a single key, like a number, you instead use a whole word, who, much like an array, can be broken up into individual characters, and those characters represent numbers, a la ASCII. So in this case, we might say that our plain text that we want to send across the field is hello world. Well, let's use a key not of 13, but of the word, arbitrarily, foobar. That is the secret that I, Alice, and Bob, someone else, have agreed upon in advance so that we can send each other a message and decrypt symmetrically that same process. So what appears to be the mapping of characters to numbers here? So H, I, J, K, L, M. So it looks like F represents 5, which makes sense if A represents 0. So you have to not only agree on the key, but on a mapping of letters to numbers. We, being computer scientists, will assume that A is 0, B is 1, and Z is ... 25. And so long as we're on the same page, so to speak, we can now encrypt something like hello world to be this crazy string, MSZMO. Notice we're not even going to bother with punctuation, though we could, but it would increase the size of our alphabet and just make things a little more confusing for discussion. So spaces and commas stay the same, but the ciphertext, so to speak, is more secure. But why? Why is Visionaire arguably more secure than Caesar? Right, you can't just shift the letters once, guess one number, and apply it to all the letters and see what pops out. But rather, you have to try instead not all possible numbers from 1 to 26 or 0 to 25, but instead, like all possible words in the Oxford English Dictionary, plus all the words that aren't even, because maybe it is these days, but foobar might very well not be in there. So what does that mean in terms of the strength or the security of this cipher? Well, Caesar, given that it had keys, a key space of 26, there's 26 possible keys. How about for Visionaire? How many possible keys are there? So it kind of depends, right? For every letter, you have for every letter in the word, you have 26 options. But then you have flexibility, it seems, over the length of the key. So if I arbitrarily decide that, you know what, keys by standard are going to be 6, well, that means there's 26 to the 6th possible keys that we might have used. But there's also 5-letter words if we don't require that the key be 26. There's also 4-letter words if we don't require that it be 26 or 5. And actually, it's sort of an infinite key space, although at some point it becomes harder to remember the key than it does to actually encrypt the message. Yeah?
So there's no real way to have a key longer than the message in the first place.
Good. So there is one implicit upper bound, which is that you can pick the longest key you want. If you're sending less information than the key, you're not going to use most of those bits. So absolutely. So this works even better the bigger the plain text is, because you have yet more options for keys. So that's kind of interesting, but there's a problem still. Well, one, even this can kind of be brute forced by computers these days, right? If I just do a quick calculation of roughly how big this thing is, I can run a program, nice math program called BC at the prompt. What's that? 26 to the 6th. So that's a lot. That's what, 308 million possible keys. But you're all pretty familiar with the gigahertz inside your own computers these days. We're probably talking a few seconds, maybe, to crack that key space, maybe a few minutes maximally. Well, what if we choose something like words that are, or keys that are 124 characters? Okay, so now that's getting impressive. But it'd be nice, perhaps, if we could sort of formalize this. So there exist your browsers these days, ATM machines these days. They don't use Caesar and they don't use Visionaire. They do use things that are more sophisticated and that can be computed ideally more efficiently. So this is just a depiction of something called digital encryption standard, which is somewhat deprecated now, but its own picture sort of hints at how it works, which is to say, you take if you've got something you want to encrypt, you take it and chop it up into 2 halves, left and right. You perform some math on the left, you perform some math on the right. You then sort of move the bits around, and you repeat this 16 times. And for our purposes, the takeaway is that's stronger than Caesar. And it's stronger even than Visionaire in most contexts. In fact, this is the total number of keys that are possible if you use DES in this way. I think that's 72 quadrillion possible keys. Certainly takes a computer longer, but right, all of us have probably read one article at some point about how some supercomputer cracked something or other. Not that hard to encrypt this, to crack this. Well, there's triple DES, 3 DES, which is essentially this algorithm applied 3 times, right? So why stop at one iteration if you can just run the thing 3 times? And that does something somewhat better. There's something even newer called AES these days, Advanced Encryption Standard, and many, many, many other algorithms still. But it's this kind of stuff that's used in browsers today, cell phones, and ATM machines and more. But there's a big, big gotcha. So you all know that if you ever bought something online, you get that little pad-like icon in the bottom corner that's supposed to say your connection's secure, and the URL becomes HTTPS. Well, what does that mean if the padlock is there and you're actually on a legit site? Well, your browser and the web server are encrypting the information between you and, say, Amazon. Now, we could assume it's something simple like Caesar, but if we just generalize and say, maybe it's just one of these secret key protocols, what's the problem with all of the protocols we've discussed thus far, all these ciphers? They assume what about me and Amazon? Yeah, that we share this key, that we're buddies, and at some point a priori we've agreed upon some secret. But you have kind of a catch-22 here. If you want to go to Amazon.com and buy something for the very first time, which is in Amazon's interest not to make very difficult, well, if you're going to encrypt information like your credit card back and forth, you've got to have some secret between you. Well, how can you get that secret? Well, I mean, it's laughable to assume that you have to, call them up and have someone whisper the key into your ear, right? Even in the real world, it'd be kind of dumb if to start sending information securely, you had to go talk to the person privately, because you might as well just tell them the secret at that point anyway, right? You don't need cryptography if you have physical access to the person. So fortunately, there's asymmetric cryptography, whereby you don't use a number that both of you have to have, you don't use a word that both of you have to have, but you're a little more clever. And it was just in recent decades where this kind of stuff was invented, was discovered. We won't go too much in this course into the mathematics. You can look at CS120 and some grad level courses if you're curious, but the idea behind public key cryptography is that each of these parties, Alice and Bob, or me and Amazon, don't just have one key, we have 2. I have something called a public key and something called a private key. And there's some neat, fancy mathematical relationship between public and private such that Amazon can use my public key when he wants to encrypt something and send it to me. I equivalently can encrypt information to Amazon by using his public key, which by nature that he and I can literally publish on our websites. We can literally email across the internet in our signatures. We can literally shout it out loud because mathematically it's totally okay for anyone to know your public key. Because mathematically the only number in the world that can reverse that process, encrypting with your public key, is, as you might guess, your private key. And so that's the only number you need to keep secure. So how does this work in browsers? Well, you install Firefox or Safari or IE, all this stuff happens for you automatically. Like they generate some big, big numbers, one public, one private, tuck that away somewhere on your hard drive, and then start using that henceforth to communicate. Well, the general depiction is here. Plain text gets encrypted with the public key, becomes ciphertext, but again, to be decrypted, it has to use this private key. And my public and private keys are distinct, but again, related. And the neat thing here too, and your sort of extra credit perhaps for a computer science program, is that many of these crypto systems are based on the assumed difficulty of factoring really large numbers or figuring out if numbers are prime. So that is to say, underlying algorithms that are public key based, like RSA, if you've ever heard it, is the use of really big prime numbers that you smash together by multiplying them together to get an even bigger number. And the reason that these ciphers are thought to be, but not known with certainty to be secure, is that man has yet to come up with an efficient, quote-unquote, way of factoring really large numbers. That is, even with really fast computers, it will take more seconds than there are atoms in the universe. That's the sort of scale that these problems are measured on, at least when you're trying to use a bit of hyperbole. But mathematically, it's true. What do these things look like? well, you saw a really big number go across my screen a moment ago. This is just another representation of the same. There's this software out there freely available called PGP, Pretty Good Privacy, which is kind of an understatement because it pretty much uses RSA, this public key crypto system. And what you do is install in your special email software a really big number that looks a little something like this. It's actually alphanumeric, but that just means it's like base 26 instead of base 10 or base 2. And this is just a hint at this kind of stuff. And the more time you spend in a computer science class, the more likely you are to get an email from a friend that is digitally signed. And those digital signatures that Outlook or Gmail will say this email has been digitally signed really doesn't say much of anything other than the person who sent it to you went through the trouble of encrypting it in part to prove to you that it's from them. Though of all my friends who do, I am trying to tread carefully here because I know some of the TFs do this. I don't really question generally who emails come from, but with this same crypto stuff, can you implement what are called digital signatures, which is to verify one's identity. And those of you who like the mathematics can take a look at this kind of stuff and certainly turn to Wikipedia. But it's in problem set 2 where you'll be challenged not only to implement one or more of these ciphers, but in the hacker edition to actually crack a number of hard encrypted passwords that we have generated for you. So with that said, no applause. See you Monday.